and we'll go in order. And so I guess the first one is Hari. Is that right?
Time is not important. However, time is important.
And
There are going to be 80 more people at the barbecue. You want to be the first 40 or the second?
Okay.
Last one there.
yeah, all right. And then I think, is that clicker? And can you advance the slides? Okay, so, all right. And you're unmuted, so, okay, all yours.
Hi everyone, my name is Hari Prashad Ravi Kumar. I'm working on calculating the X dependency of the Sieverts shift from lattice QCD with Dr. Michael Engelhardt from New Mexico State University. Let's dive in. So we have all seen this. It's a bilinear operator with a clock separation. Oh, not this one.
It's a little slow.
Okay, pick it up. With the clock separation B and with the Wilson line that connecting the quarks. And if I do the Fourier transform and if I integrate out the X minus, then we get the correlator in as a function of longitudinal momentum fraction and then the transverse momentum here. And this is something like number operator of the quarks. So we can count the quarks in various ways by using a different gamma structure. For gamma plus structure, that will decompose into unpolarized TMD and then the Sieverts TMD. And one can do the same thing in a position space. So I'm starting with the position space correlator and I'm doing the same decomposition for gamma plus. Then I get this A amplitudes. These are kind of like a Fourier transformation of unpolarized TMD and then the Sieverts TMD. And I do have to talk about the gauge link that we are doing. And we are not going to do the straight gauge link that just connecting 0 to B because we are interested in the Sieverts shift, where those are time odd functions. So having this staple link going this way and then going opposite way will give the siders and then Brillouin limit. The staple link is from 0 and then going in a light front direction B or close to light front. And then again going back and then connecting back to B here. So what this physically means is we hit a quark. It's a deep inelastic process, and the kicked quark is going in a light front direction, at least close to the light front direction, and that's the V direction. And we parameterize with the eta, and the eta has to go to infinity, but the lattice we can only go as much as the lattice, the size. So we will have like a bigger eta value, and we won't keep the V direction in light front direction. We keep it in a space-like direction, but one can take a limit going to the light front. There is a way we parameterize this zeta hat. This is a colon super parameter. We divide with this 2 times the mass of the hadrons, and that gives that tells us how much our staple is away from the light front direction. So we eventually have to take a limit that the zeta hat going to infinity. This is one of the limits that we will eventually do. And yeah, in terms of lattice setup, we have a creation operator, and then that's a source, and then the sink, and then we do the operator insertion at some time t, and the operator is the Wilson loop, the Wilson staple connection with some gamma structure, and we do that at a single time. So that means like going to Minkowski to Euclidean space, it's like 0 times I, so that there won't be any problem. And we eventually take this eta going to infinity. That's the staple link going infinite direction coming out or going in. And then this zeta hat going to infinity, that makes the staple link going in a light front direction. All right. So far in the calculation that my advisor and his collaborators did, they were doing X moments of the Sieverts function or the other TMDs. So the way they have been doing were, you can notice one thing, that this X, longitudinal momentum fraction, and then the B dot P are the Fourier conjugate variables. So if I choose my staple connection in a way that this B dot P equal to 0, that means already it's doing a X integral. And for my thesis, we are interested in finding this X dependency of the Sieverts shift. So we have to do the Sieverts TMD in the position space, divide by the unpolarized TMD. That's a ratio that we form, the Sieverts shift we call. And we eventually have to do this, the Fourier transformation. That means we need to have a lot of values kind of like that scans all the B dot Bs. In a way, we could able to fit it to a function, and then we can analytically able to do a Fourier transformation. And that eventually gives the Sievert's shift as a function of X here. And for example, this one, the ratio that I'm forming here, here there is something like the parenthesis one. That means I'm doing a derivative with respect to V perp that will kick a ky in front. So it's kind of like expectation value of the transverse momentum here. So what the Sievert shift is like, this is a transverse momentum distribution of a quark, unpolarized quark inside the transversely polarized proton. So imagine a proton that like a polarized in this direction, Z direction, and then the proton is coming in x-axis. And what we are measuring here is that how much of the quarks are moving in this way than this way. So that's the expectation value that we are calculating as the transverse, the y component or the x component. This A amplitude that we are doing, this TMDs in the position space, are functions of various parameters. We can see all of them are like a Lorentz invariant quantities, but all of these quantities are connected with some constraint that I pointed out here. So when I'm going to form my staple link that going in non-zero B dot B, then I had to respect this constraint. And that's where the problem comes. So that will give various systematic uncertainties, particularly when you're trying to extract the small x and then other things too. For example, if I try to solve this constraint and then I look for what kind of direction I need to choose for my staple, one of the example is something like this. So my staple is no longer going in a straight lattice direction like x or y direction. It's now going in off-axis direction. And the way we approximate that in terms of in a lattice, like using this kind of staircases, like each staircase is like gauge link connecting in this way. And this is just a choice that I made here. Eventually, when we do the analysis, we had to make a more than various forms of staircases, and we had to approximate, like take a average over it. Or some cases, for example, the one that I showed earlier, the value for the B in x-axis is like a 3.12, and in the lattice we can go to the 3.12 value. We can either go to 3 or we can go to 2 or something. So in those cases, I had to interpolate between 3 and then 2 here. So there are various analyses that we still need to do. This is still in a preliminary stage, and this is just a one set of like a stable connection that we can form. In most general, okay, before going that, yeah. So then once I have the stable connection, and I can extract the gamma plus 3-point function, and that gives the real and then imaginary part. The real part is directly the unpolarized TMD in a position space, and then imaginary part gives the Sievert's TMD in a position space. So we can see these are already an even and odd function in terms of eta. Eta is the direction of the staple link going, and we will eventually extrapolate eta going to infinity. So we will be having this side sinus and then this side Brilliant limit we will be having. So we eventually have to make a
minutes, so we're at 8 minutes.
Yes, almost done. So yeah, as I mentioned, the one that I showed, the whole staple link on a single plane was just a one particular choice, and that's with just one data we really can't do any Fourier transformation. And the most general one looks something like this. So the staple link kind of in a 3-dimension just comes out of a plane. It's no longer going to stick in a one plane. So that makes the process even more complicated. And yeah, so we do have some preliminary data. So here I have the ratio from Sievert's shift to Sievert's TMD to unpolarized as a on the left-hand side. On the right-hand side, I just have a Sievert's function as a function of longitudinal direction in B. And yeah, with that data, we did extract the preliminary calculations for the Sievert shift multiplied with the momentum fraction and as a function of x here. And this is just for me to figure out like my results that I will get out of my thesis should lie in between this error region here. And to conclude, it is feasible to now extract the x dependency of the TMDs. So for now, we are trying to extract the Sievert's function, because it's quite easy to calculate from the lattice. And if we figure out like it is at one way it's straightforward to figure it out, then we will extend the results to other TMDs as well. And with that note, I would like to finish my talk and I'm open for the question. Thank you.
How do you do renormalization?
Oh, we don't. Right, so so far the calculation is already complicated, so so far we are just stating it as a the lattice result here. And I guess I had to verify that because we make a ratio with the sieverts to the unpolarized, and already this renormalization value get cancelled when we form the ratio. And I'm not sure, I had to check that thing. But one thing I know is that we're not doing renormalization. We're just stating the lattice result. No.
Okay, all right, let's thank Gary again. Next. Okay. All right, go ahead. The lower one will take it back, right? Yeah, the
Okay.
one is a little slow.
Okay. Oh. Okay. Hello, good afternoon. My name is Hoyeon. First of all, I appreciate organizer allowing us to present our recent work. I work with my supervisor, Sadi Rose. Today, I will talk about special distribution of the energy momentum tensor inside the nucleon. So what is nucleon? It is main building block in the visible universe and a complex object composed of quarks and gluons through interactions such as strong, weak, and so on. On the right-hand side, you can see three valence quarks and a number of quarks and gluons. Of course, it is not real photo. So in the present work, we use form factor in order to study internal structure of the nucleon. Form factor gives information on spatial distribution and its radius, such as proton charge radius. So form factor is a kind of structure function due to the compactness of the particle. In this diagram, we can see the form factor at the vertex. So the spatial distribution, it can be defined by Fourier transformation in the form factor. However, we face a relativistic challenge. Comparing reduced Compton wavelengths and proton charge radius, we recognize relativistic effect is not enough to neglect, such as 25%. So it indicates the internal dynamics of nucleon is fully relativistic. In addition, we have to consider the frame dependence for the spatial distribution. So we consider relativistic amplitude. For spin zero particle, the Lorentz transformation amplitude is rather trivial, as you can see. On the other hand, for higher spin cases, such as one-half particle, complicated structure appears. We have to understand relativistic spin dynamics. So let me start at initial state with zero momentum. We act Lorentz boost and Lorentz transformation, so we can get the P prime S prime state. Then we can act inverse transformation. However, we couldn't come back to the initial states. So it comes from non-commutation relation between two different generators of Lorentz boost. So on the right-hand side, total angular momentum leads to Wegener rotation in the final state. So, and we also introduce elastic frame. It is a connection between the elastic frame and moving frame. It describes both bright frame and infinite momentum frame. As you know, this infinite momentum frame is comparable for light frontal frame. So regarding both formalism, we deal with energy momentum tensor. It is conserved current under space-time translation. It includes energy, momentum, normal force, and shear force inside the system. So here on the right-hand side, I bring our preliminary result on energy distribution for transversely polarized nucleon along the x-axis. So in the bright frame, you can see the center of the system on the center of the impact parameter space. On the other hand, we increase PZ, then the distortion appears. Finally, in the infinite momentum frame, the distortion disappear and the center of the system still located at the center of the frame. So for the future work, applying for our formalism for higher spin hadrons such as delta variable, etc. And we would like to study transverse total angular momentum and orbital angular momentum distributions for nucleon. I mean, unpolarized nucleon or polarized nucleon. Thank you.
Some questions?
Ninth question. So the last picture, you mean after you boost the Z direction, there's no shorting things, no contraction?
Yeah, actually it is on 2D space. I mean, impact parameter space. Yeah, actually introducing elastic frame, you have to pay. So that means we lose the longitudinal information.
Okay.
Yeah.
Other questions? If not, let's thank you. Thanks. Bottom lower one will take you back.
Hello everyone, myself Ankush Sharma. I'm working on the spectroscopic analysis of exotic hadrons using effective theories. Exotic hadrons are basically tetraquarks and pentaquarks, and they do not have the conventional structure of meson and baryons. So basically, tetraquarks are exotic mesons and consist of pair of quarks and antiquarks, whereas pentaquarks consist of 4 quarks as well as an antiquark. Recently, we experimentally detect few of the tetraquark and pentaquark states at LSCB and etc. So basically, to start with the classification scheme, we classify them using the special unitary representations and the Young-Temple technique. So by using the SU3 flavor, we assign each quark by a 3 and an antiquark by a 3-bar representation. So as I have shown, we can classify the fully light and fully light pentaquark and tetraquark state into the different flavor multiplieds. Similarly, for the spin, we use the SU2 spin representation, where we assign each quark as well as an antiquark by the 2 representation, and we get the following spin multiplieds. And again, Young-Temple technique. We can define spin flavor wave function using the Young-Temple technique, where we make use of the Young-Temple. Here, in each SU1 representation, we denote a quark by a box representation and antiquark by n-1 boxes in vertical manner, as I have shown for the different special unitary representations. So by using these schemes of special unitary representation and Young-Temple, we classify the exotic hadrons into the different flavors multiplets. So these are the 3 different methodologies I have used. For estimating the masses, I use extension of GR mass formula and the effective mass scheme. And to calculate their magnetic moment assignments, I use the effective mass and the screen charge scheme. GR mass formula is initially given for the baryons. So we extended this to calculate the masses of exotic hadrons like tetraquarks and pentaquarks. So it was initially defined in terms of the Casimir operator for the spin, hypercharge, and isospin. So by considering the chiral quark model, we consider the underlying symmetry of SU6, where the spin flavor symmetry has been considered. And then by putting the eigenvalues for the Casimir operator of the respective quantum numbers, we get this mass formula. And then we extended this to consider the contribution of heavy quarks, such as charm quark and bottom quark. And in the table below, we can see the mass formula parameters, which are constant values and shown with their respective uncertainties. Second one is the effective mass scheme. As we can see in a hadron, the mass of the quark influenced by the respective quarks and its neighbors. Similarly, we extended this for the pentaquarks,
where mass of pentaquarks is defined by the sum of the quarks as well as their hyperfine interactions with the respective quarks. Bij are the hyperfine interaction terms, and these are the equations defined here below for the respective quarks. By adding them and by taking the masses from the experimental activities, we can estimate the hyperfine interaction terms. And by using these terms, we can estimate the masses as well as the magnetic moments. Second one is the screen charge scheme. As we defined for the mass, a similar effect we can see with the charge of the quarks due to the surrounding. So we define the effective mass equations. These are the linear equations, and we have different screening parameters for the respective quarks. And then by adding them and calculating, and by considering the isospin symmetry, we can reduce the parameterization. Also, by considering the spatial unitary representation, we further reduce these parameters. And then by using the Ansatz formalism, we calculate the screening parameter. And by using these three methodologies, these are few results. We have classified the hidden jump pentaquarks into the decouplet representation, having spin 5½ And these are the expression for the decouplet particles for their magnetic moments using the effective mass scheme. The table above shows the mass spectra, and the table below shows the magnetic moment assignments using the three different methodologies of effective mass, screen charge, and both of schemes together. And again, we have also classified the hidden bottom pentaquarks into octet and the decouplet representation, and the respective results are as shown as that. We also studied the singly heavy pentaquark structures, and results for their masses have been shown. Thank you.
So, I mean, you've extended this to the pentaquark case. So, I mean, it's been a while since I looked at it. What's the characteristic accuracy set aside the pentaquarks if I just do this for the normal states? And then what kind of uncertainties? I mean, we're talking 1%, 10%. What are the characteristic uncertainties?
Well, I compared my analysis with the experimental available data, and it shows good agreement with that. So that's why we extended here.
All right, yeah, it's been sort of fun to see the OACB results come out on this. So, yeah, it's sort of a new area. Any other questions? No, let's thank him again. And the big one goes forward, the lower one goes backwards, and the pointer takes a while. It's a little slow.
Okay. Hi, my name is Sang Yong-son from Korea National University in Korea. So I am currently working on the generalized Harton distributions in the presence of nuclear resonance state under the supervision of Professor Kirill Semenov. So since this is a very short and live talk, I will focus on what am I studying and which approach I am using. So 3D structures and the mechanical properties such as spin distributions and shear forces for the ground state nucleon has been extensively studied so far. But while this kind of properties for the baryon resonances, we haven't yet studied much. Because the nuclear excitations like delta baryon or any other n-star states cannot be a target particle, right? So we access them through the non-diagonal hard reactions where the transition from nucleon to the resonance occurs. In that case, we get to access to the so-called transition GPD. And such kind of processes can be further extended within the framework of the N2 and pi GPDs, which where there is subsequent decay into two hadronic state like nucleon and pion as delta and other excitation state decays. And I want to emphasize this kind of hadron to two hadron system GPDs have much more complicated structure. Like first of all, it depends on many more variables than the usual GPDs. Like it depends on the invariant mass and decay angles of the final state hadron state. So especially the invariant mass of these GPDs may provide information on its nuclear resonance spectrum. And this end-to-end pi study is very complicated mathematically. So first, we focus on the toy model involving only spinless hadrons, which is the pi2, pi GPDs in the certain resonance state. So this can be a kind of a precedent work for developing the framework for the hadron resonance spectroscopy. So our present work aims to establish the transition GPDs as a very useful tool for studying the kind of hadron resonance spectrum. So yeah, in particular, I included manually the low measure contribution to the pi2 pi GPDs and also its effect on this cross section. And we were able to find the proper rules for a partial wave expansion to this pi2 pi GPDs. And yeah. So with some phenomenological models, we were able to estimate the cross section for this pi2 pi non-diagonal process. Of course, in principle, we have to access this kind of process through the Sullivan type of process. So here you can see each contribution from the Bethe-Heitler and DBCS process and in different value of momentum transfer. So you can see in the case of pi2 pi cross section, the DBCS contribution is dominant more than the Bethe-Heitler as a low value of momentum transfer. And the below diagrams is the contributions from the longitudinal and transverse helicity of intermediate low measure state. So at the low value of low T value, the longitudinal helicity low measure is more likely to be produced in the intermediate state. Sorry. So that our pi2 pi GPDs can be studied also in the threshold region with the very basic chiral dynamics such as soft pion theorem, and in that region, these pi2 pi GPDs, its hadronic matrix element for the light cone curve operators can be reduced to the chiral rotation of the same operator, but with respect to the diagonal pi2 pi matrix element. So these pi2 pi GPDs in threshold can be constrained in terms of very well-known pion GPD. Also, in the resonance region, which we are interested in, the imaginary part of the transition GPD can be developed. So this is what I want to emphasize. Unlike the usual GPD, the GPDs for the hadron to two hadron system can have an imaginary part. So that imaginary part is given by this discontinuity along this cut, and the GPD, that imaginary part of GPD is obtained by GPD itself and convolution with the pi scattering amplitude by the Watson's final state interaction theorem. And this imaginary part provides the distribution in invariant mass of pi system. So yeah, that's it for my short talk. And although my slides end here, I would like to introduce some another interesting quantity which is so-called Prasad-Grigor projection. So if you are interested in that quantity, then we may discuss at the barbecue party. Yeah, thank you very much.
So as Becky had the beta height horn, the DVCS, so the angle, I mean, the angle is crucial here. So
Yeah, this is an angle distribution.
yeah, because that, I mean, that allows you to really separate the two components and focus on,
Yes.
yeah, so that you want, okay. So you, I mean, basically you want to work at sort of the extremes endpoint to kind of get out the,
Yeah, it is quite interesting result, but unfortunately, it's the cross section has a low value, and experimentally we have to consider the nucleon target like a Sullivan process, so it could be lowered. So yeah, but this is not our message. Yeah, our message is approach for this.
it's challenging, so.
Yeah.
All right, other questions?
Yes, thank you very much.
Marty, and all set, okay. Yeah, the big one will move it forward, the one below will move it down. And the pointer's a little slow.
Okay. Hello, everybody. I am Bart Chuni. I come from University of Manitoba and I work with water deconic. So the topic of my research deals with leptoquarks, basically optimizing the background simulation for charged lepton flavor violations. This is basically a work that initially started with the ECHE, which it was also the proposal that Professor Deshpande mentioned. So we are just moving this work further, of course, in aspect of epic configuration. Before jumping to the topic, we know that with neutrino oscillations, how they lead to lepton flavor violation, and of course, through loop processes, we can go to charged lepton flavor violations. The branching ratio, for example, for charged lepton flavor violation within standard model 10 to minus 54, and this was suppressed, but people have worked through that and enhanced this. For example, when it comes to charged lepton flavor violation from first, for example, from electron to tau, people working in HERA, Babar experiment, and LHC, they have enhanced the rates so that the motivation is higher, so that we work for searches for electron to tau transition within also EIC, because EIC, beside working in a strong, let's say, interaction or QCD, also is a good environment or a good experiment, which will lead us to beyond standard model measurements. So my work is basically based on this process, deep and elastic process. As you can see, electron plus proton to tau plus, let's say, jets, and but it's in the leptoquark framework. My work basically deals just with the simulation. It's not work that deals with theory, because this is something that can be done also in theory if someone works in standard model effective field theory and dealing with 4 leptonic interactions, and of course, dealing with the leptoquarks. Leptoquarks, so are triplet bosons, as you can see, even from the name, they couple lepton and quark. This is something that we don't have in a standard model. So right away, we have an idea that this is a theory which deals with the beyond standard model physics. So in our study, mainly, like I said, we look for electron to tau transition, but we cannot detect the tau because it decays directly on our detectors. But the decay or final states that we are interested are the 3 pions. So in our study, the hadronic tau decay which will be focused would be on a pi plus, pi minus, or could be another 3 pairs of pions. It could be pi minus and 2 positive ones. But basically, when we have a leptoquarks in our case as an event, there are standard model backgrounds. And these standard model backgrounds mainly come from neutral current and charge current, deep and elastic scattering, and photoproduction, which we have seen diagrams pretty often during all these talks. and they mimic the signal. So the idea in this work with simulation is to distinguish the leptoquark events from the backgrounds. For event generators that we use to produce the leptoquarks, we used LQGenApp, and for Django, we have used the updated version from last year. Usually for Django, we use to produce neutral current and the charge current deep and elastic scattering simulated events, while PTS6 is used for photo production. Just to have an idea or a general idea of my work, so like I said before, the goal of this work is to search for this transition between electron to tau, and of course, based on the detector simulation, and of course, dealing with the highest collision energy, 18 multiplied by 275 GeV. So, and the idea is to differentiate these leptoquark events from the background. This is just a simple picture, as we can see here. We have to start with the background event simulation, which already have it. For the NC, NCC, and photo production, we have increased the number of events up to 10 million. 1 million is what ECHE did, and they try to apply the selection criteria. What are the selection criteria? So, for example, like I said before, tau decays into 3 pions. Pions are measured in the detector, and they are within the range that we call, for example, a cone. And let's say this cone is delta R, which is in azimuthal, and the pseudo rapidity space, which is a square root of delta phi squared plus delta eta squared. And this is smaller than 1. This is, for example, one of the selection criteria that we use to identify these transitions, but there are more than one. It's a missing PT, and there are different range. We look for 3 pion PTs and so on. The idea is that when we apply the selection criteria, we want to go to some discriminating variable because we want to increase the signal over background ratio. This is very widely used technique in high energy physics. For example, as an example, we can mention D0 collaboration. When they mention single top quarks, they use machine learning technique. And this is basically the idea behind my work. We will try to use boost decision trees so that we increase signal over background ratio, and of course to try to separate leptoquarks events from the background, which are coming from the standard model, NC, CC, and photo production. So the idea is to use machine learning on the increase this, let's say, signal over background ratio, but then a leptoquark framework, always searching for these 3 pions inside the detectors. Thank you.
Questions? So, I mean, Yulia was mentioning the leptoquark channel. Have you looked at what order of magnitude you would need to see this? I think she was talking hundreds or something like that. Is that?
You mean the Q squared?
Yeah, no, yeah, I mean, the number of events to.
Oh, actually, ECHE did, like I said, simulation. They just did 1 million events, and they tried to look for the events if they pass the selection criteria. From the events, we have just CC, which 9 events passed the selection criteria, and NC didn't pass neither the photo production. So that's the idea. So we try to increase the statistics to 10 million events so that we look when we apply the selection criteria, because the number of events is always reduced when we apply the selection criteria.
Okay, it's quite a reduction. So. Okay, cool.
He's asking is that how many events could you imagine seeing, assuming certain probability of happening? In those papers, you will see those numbers. A range that relates to the total luminosity.
Probably
We can
this
talk.
was also, yeah, this was also, I didn't do the homework. Yeah.
But especially, I mean, the lepton flavor changing, that's quite interesting. Particularly, I mean, in the DIS mode, you have very clean channels compared to other things.
So if we can do better than 10 to the minus 4, we're already doing better than the world's best estimate for E to tau.
Mm-hmm. Okay.
So that's why we think it is feasible. Yeah.
Thank you.
Good questions. Thank Brady again. Thank you. Right there.
So in this short talk, I want to talk about about my work, which is the collinear matching relation for quark and gluon TMDs. I haven't tried on these slides my supervisor, which are Barbara Pasquini and Simone Rodini, with which I'm working on this topic. Okay, so short review of what we have seen with Alexei in the first two lectures, since we have the background to understand or try to understand what I'm doing. So we know that TNDs are distribution related to the three-dimensional structure of the nucleon, and particularly describe how the momentum, how the parton carries the momentum of the proton inside the nucleon. Okay. So this distribution describe processes that are related to low transfer momentum processes, low with respect to the scale, to the hard scale of the process, that is the transfer, the momentum of the transferred photon. We have seen that we haven't no first principle derivation about the analytical form, in the sense that we have seen that the TMDs derive from the composition of the correlator between over a basis of the Dirac structure, but the composition doesn't say anything about how this distribution are made in an analytical form. So we have to extract this distribution from the data, and the only way we have to extract this distribution from the data is to put some constraints on the functional form. And collinear matching relation try to reach this aim. In particular, we can see that a TMD can be written as the sum of the TMD can be written as the sum of the with the sum of a collinear PDF multiplied by matching coefficient, which are what I'm trying to calculate. In particular, we can see that there is only one collinear distribution that contributes to the TMD, but there can be a sum of. Okay, I'm not giving all the detail of the technique, mathematical technique that you are using, but just some feature of this technique that is, okay, it correctly reproduces known results. That is obvious because we have the technique that have to obtain results that are known at the scientific community. In particular, it recovers the results that obtained with other technique, but also the sign change from TOP distributions. Then here, this technique is model independent in the sense that we start from the operator given by the QCD, and we don't make no hypothesis about the structure of the nucleon. So we start with the QCD operator and work mathematically on this operator. Then this technique gives all the correction, the mass correction to the TMDs, in the sense that the correlator we have seen with Alexei is universal for all spin 1/2 particle, but spin 1/2 baryons, but baryons have different masses. So this correction take into account the different mass of the baryons that the correlator can be applied to. And also, we have that the technique is independent from spin, twist, and quark and glue. It's dependent from the spin because we can use the same technique for calculating matching relation for unpolarized, polarized nucleon, unpolarized, and polarized partons inside the nucleon. We can use, the technique is initially developed for twist 2 for distribution. You have extended to twist 3 distributions, and you have extended it, we are extending it to gluon sector. So in this sense, it's dependent from both quark and glue. I show you some results about the twist 3 results that you obtain for the quark distribution. We can say, you can see, okay, we can see the leading term. Okay, in the first, okay, but you can just point. Okay, the first term, which is the collinear PDF. The first term can be very simple when the TMD has a corresponding collinear PDF.
or can be a more complicated, okay, a complicated convolution when there is no corresponding TMD, PDF to the TMD. This for the one of the sector of the field of the field can remind the Van Zura-Wilkes relations, but okay, in this case we are at twist 3, and for complete this relation we have to go to twist 4, that is mostly unknown, so we have stopped our calculation to twist 3, and then I put an example of mass correction. We can say that are depend in particular on x squared, m squared, b squared, but in many experiments, m squared, b squared is near to 1, so this term, and since TMDs are extracted near, for example, x near 0.1, this series in many cases is suppressed. But when experiment in which this term is not suppressed can be useful for extracting also even this from other type of variants. Okay, I just said that these results can be useful for studying higher twist contribution to processes, in particular in those regions where the leading twist is not enough to describe correct data. And now what I'm working on, okay, we are working on with also Nanako and his and her supervisor. We are working on the gluon TMDs, extending this technique to the gluon TMDs. This is the actual level of knowledge about matching relations. The score indicate that we are sure that these results are 0. And so, yeah, as you can see, you don't know anything about the gluon TMDs apart from the unpolarized hadron and the ECT. Our aim is to fill all the gaps, surely at 3 level, and at 1 loop for those TMDs where the hardness of a calculation is compensated by immediate applicability in phenomenology. So I left the references where this described the technique and our article, mine with my supervisor, the collinear PDF with a collinear matching for the twist 3 distribution. Thank you.
Allow me to go back to the equation. And yes, the question is, so the correction term, you got the x squared, m squared, b squared. So m that's like a JEV.
M is the mass of the barrier. In particular, for the proton is obviously 1 JEV, okay. But you can apply this formula for all baryon that have the same, all 1/2 spin baryon that have the same correlator as the proton one.
Okay, and then the x squared factor, so that gives you, yeah, so it's
the x that is measured experimentally. So in particular, at the moment, we cannot use this formula for extract twist 3 quark TMDs, since we are not able at the moment to have the data to extract the distribution. But we are using these formulas, for example, for making prediction, since we know how the structure functions are made, so we can see how what structure function can dominate at 3 level in the series process when we go to the twist 3 contribution.
So I think this is going to be a blackboard. You want to use whiteboard, blackboard, or
whiteboard is
okay. And not sure. Does anyone know how to move the camera?
It tracks, but I'm.
Yeah. Oh, it's yeah.
Even the
The camera will follow you. You were good. Okay.
As long as you speak.
I will speak. Just check. Okay, perfect. Hi, everybody. My name is David. I'm finishing my PhD right here in this building. And first, I'd like to thank the organizers for putting together this very interesting school. And I also want to apologize to the organizers and lecturers for missing most of the talks.
because when I signed up for the school, I actually didn't know that I would defend in a few weeks from now. So the time is a bit unfortunate for me. But I will just flash you some ideas, and I will try to be provocative deliberately. So you can come and find me at the barbecue. I should be in the grilling area, so I should be pretty fine to find, pretty easy to find by smell. So come and find me at the barbecue. Okay, we have heard today that we still don't understand where do the spin and the mass of the baryons come from, and that's the reason why we are building this nice machine. But I will go even further and ask a seemingly stupid question. Do we know where does the baryon number come from? Which degrees of freedom in a baryon, which is made out of quarks and gluons, carry a baryon number? At first sight, you may say, well, the baryon, is made out of 3 valence quarks. Let's try to see what can be a QCD operator to describe a baryon. We should have some quark fields at some different points, x1, x2, and x3. So we have a product of 3 quark fields. Okay, this seems good enough. We have 3 quark fields. Maybe each of them carries 1/3 of the baryon number. End of story. Well, let's not be so fast. Let's remember that in QCD, we must have gauge invariance. What happens to this guy if I do a gauge transformation? Well, they transform differently, right? So this one transforms under gauge transformation at point x1, this one at point x2, and this one at point x3. They all transform differently, and you cannot make a gauge invariant like that. You need to do something else. What you can do, we know that we can transform the point in which gauge transformation happens by attaching a Wilson line. So we can actually attach a Wilson line to first quark. So it will connect some point x and point x1. And then also to the second quark, it connects x and x2, and to the third x and x3. And these composite objects, which are made out of Wilson line plus a quark, transform all under the same point x. So it's already getting somewhere. Now you just need to anti-symmetrize with respect to color, and you will be done. It will be a gauge invariant object. So what did you get? We have 3 quarks, x1, x2, and x3. And we have introduced an extra point, x. And we have connected this point by Wilson lines, like this. So we have 3 Wilson lines joining at a point, and this is in fact called a junction. It's a junction of Wilson lines or a junction of strings if you treat these Wilson lines and strings in a dual language. So this object is also called a baryon junction. Now, I will claim that it's a natural thing to associate baryon number. Because let's look at what happens if you try to separate the quarks from the junction. Let's say that you take this quark at x3 and you start pulling it away. As you pull it away, the string stretches and eventually the string breaks. It's the usual strings fragmentation. And as it breaks, you have a meson formed here. But then the quark, so there is anti-quark that goes into meson, but quark stays attached to the initial junction. And if you try to do it by pulling all of 3 quarks away, baryon will still be restored around the junction. So junction is a natural object to which to associate, more precise statement would be that it's a natural object to associate the flow of baryon number in high energy reactions. So if you hit the quarks very hard and they fly away, fragmented strings will fragment in such a way that the baryon will be restored around the junction. How to test this experimentally? So this will not be very detailed. I'll just show the main idea, and feel free to ask me more questions. We can look, for example, at deep elastic scattering, where we have, as usual, an electron exchanging vertical photon is a proton. So this is a proton, and the proton has 3 quarks. But now I want to also highlight that I have this additional dynamical degree of freedom in the junction. So I will put it in this dashed line, so the dashed line stays for the junction. So this photon has to interact with some of the degrees of freedom, right? So let's say that I will be tracking some baryon in the final state. So it will be semi-inclusive deep elastic scattering. So I will have gamma plus proton goes into baryon plus X. So if the junction picture is correct, then this junction from the initial proton has to travel somehow to the baryon. And then it may be accompanied by some of the valence quarks, or it may actually not be accompanied by any of the valence quarks. So in this case, all the valence quarks will just go in the proton fragmentation region, and here we will have some dynamical production and some new quarks will be born and populate this baryon. So you immediately see that if this picture is correct, the baryon is completely decoupled in terms of flavor from the initial proton. It can be of any flavor. It can be made out of 3 s quarks, for instance. So it can be an omega. And you wouldn't have that if this baryon would have to inherit some of the initial valence quarks from the initial proton. So there is also already a clear prediction that if you observe an omega here produced, this is a clear signature of the junction. But moreover, there is a prediction also for how these baryons will be distributed in rapidity when they are produced at large rapidity gaps from the initial proton and the virtual photon. Essentially, this analysis can be done in registry theory, and in registry theory, you would look at a cut in T channel, and you will see what is exchanged in T channel. So in this case, you will see that it's just the junction here, and then when you take the complex conjugate amplitude, you will have an anti-junction. So the object which is exchanged in T channel here is actually an exotic blue ball. It's made out of junction and anti-junction, which are just connected to each other by 3 Wilson lines. This is a nice exotic object that you can build in a theory with junctions. It's completely gluonic, and it's what is exchanged in the T channel of this square diagram. Then you can try to work out some predictions for what should be the Reggie intercept of this trajectory corresponding to this exotic blue ball. This can be done, and this leads to some particular prediction for the rapidity distribution in the final baryon. So basically, you look at the distribution of baryons in their rapidity, and it goes exponentially with this final rapidity, and prediction is minus 0.5 for the power of the exponent, and it's different from the one that you would get if there was no junction in the picture. So this distribution can be measured, and you can check whether the exponential is what it is predicted by this or by other pictures. Okay. Let me stop here. Yeah.
Heard the question, what is the baryon number, but I just didn't get the answer.
Well, the question was what carries the baryon number, right?
Okay.
And according to this picture, what I was trying to explain, that the natural thing to associate the baryon number with is this baryon junction. So you can argue that the baryon would always be restored around the junction when you pull away the valence quarks.
Any other questions? No, let's thank David.
I have one.
Oh, go ahead.
Can you reconstruct? I mean, I understood what you did here, but I don't know enough to negate the possibility of having those 3 gluon lines directly connecting x1, x2, and x3 in a triangle.
Well, the triangle is not feasible from gauge invariance.
I see.
Because from gauge invariance point of view, if you have 2 quarks, you cannot really connect them by Wilson line. It wouldn't be a gauge invariant object.
Okay, I see.
So triangle here is actually excluded from the get-go.
Okay, I see. So there is no other way. This is the only way.
Yes. The real question is whether it has dynamical implications or not, I would say. So that's a question that needs to be tested. But theoretically, that's really the only possibility. It's just the question is whether this fancy and fundamental property of QCD actually gets reflected in real collisions.
Let's thank David again. And again, thank you to all the speakers. So now that you see what people are working on, you'll have a chance to chat with them over the barbecue and next week. And again, we've got a few slots for next Friday. If you'd like, please send me and I'll put you in. I just got a text that the grills are up and running. My brother's down there flipping burgers. And so go ahead and pack up your stuff and most come down. We'll see you guys.
Oh, okay, very good.
So
Have a
actually,
fantastic weekend, relax, decompress, and then we'll see you right early Monday, ready to go. Barbecue starts now. Whatever you want.
Did I come and check out? Yeah, that'll be a separate celebration.